Hello everyone. Today we are going to analyze this frame. In this frame, there are two columns, column AB and column CD. Also, there is a beam BC. In the columns, there is no load. In the beam BC, we have a uniformly distributed load 30 kN per meter. It is acting for the full span. In the joint B, there is a nodal point load 45 kN. It is acting towards the right side. The height of the columns are 4 meter and the length of the beam is 5 meter. For the columns, the moment of inertia is I, and for the beam it is 2I. In the points A and D, there are hinged supports. In this frame, the number of unknown reactions and moments are 4. In the point A, we have the horizontal reaction HA and the vertical reaction VA. And in the point D, we have the horizontal reaction HD and the vertical reaction VD. So the total number is 4. The available equilibrium equations are 3. The degree of static indeterminacy will be 4 minus 3, so it will be 1. Let us keep the horizontal reaction HD as the redundant. To find VA, let us take moment about D. In this case, we have to follow right hand side rule. VA is acting in the clockwise direction, so that it will be positive, and the distance is 5. So 5 VA. The UDL is acting in the anticlockwise direction, so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. The nodal load 45 kN is acting in the clockwise direction, so that it will be positive and the distance is 4. For VA we will get 39 kN. By applying this rule, we can find VD. For VD, we will get 111 kN. Now let us apply the rule sigma H is equal to 0. This load is acting towards the right side, so we have to keep HA and HD towards the left side. Since 45 is acting towards the right side, it will be positive. HA and HD are acting towards the left side. Both of them are negative. For HA, we will get 45 minus HD. We know the formula for the strain energy due to bending. In this frame, we have to make sections. There are three different parts, A, B, B, C, and C, D. So we have to make three sections, one in AB, one in BC, and one in CD. You can see that I have made three sections, one in AB, one in BC, and one in CED. This section I have made at a distance of x from A. This section I have made at a distance of x from D, and this section at a distance of x from C. Since there are three sections, we have to split this formula into three parts. This is for this section. The limits will be 0 to 4. This is for this section. The limits will be 0 to 4. And this is for this section. The limits will be 0 to 5. For BC, the moment of inertia is 2I. So in the formula, instead of I, we have to apply 2I. 2 into 2, it will be 4. Now let us find M1. Up to this section, we have VA and HA. For VA, there is no perpendicular distance, so we should not consider this. HA is acting in the clockwise direction, so that it will be positive and the distance is x. We can multiply this with this so that we will get this. We have to partially differentiate M1 with respect to HD. In this term, there is no HD, so the differentiation will be 0. For HD, the differentiation will be 1. So minus 1 into x, it will be minus x. To find M2, we can use the left-hand side rule. Up to this section, we have VD and HD. For VD, there is no perpendicular distance, so we should not consider this. HD is acting in the clockwise direction, so that it will be negative, and the distance is x. We need to partially differentiate M2 with respect to HD. For HD, it will be 1. Minus 1 into x, it will be minus x. Now let us find M3. Up to this section, we have HD, VD, and the uniformly distributed load 30 kN per meter. HD is acting in the clockwise direction, so that it will be negative, and the distance is 4. So minus HD into 4, we will get minus 4 HD. The vertical reaction VD is acting in the anticlockwise direction, so that it will be positive, and the distance is x, so 111x. The UDL is acting in the clockwise direction, so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. We have to partially differentiate M3 with respect to HD. For HD, it will be 1. In these two terms, there is no HD, so the differentiation will be 0. Minus 4 into 1, it will be minus 4. When we partially differentiate the strain energy U with respect to HD, we will get the horizontal deflection at D, which is 0. Let us partially differentiate U with respect to HD. When we partially differentiate these with respect to HD, we will get these. We can eliminate 2. 1 upon EI is common. We can take it outside, and on the other side, 0 into EI, it will be 0. Finally, we will get this. Here, let us apply the movements and the differentiations. We can multiply these two terms, we will get this, and we can multiply these two, we will get this, and finally we can multiply this with this, so that we will get this. After integrating and simplifying, we will get HD, which is 30.06 kilonewton. For HD, we have got a positive value. That means our assumption is correct. We assumed that HD is acting towards the left side. Since we have got the positive value, it is really acting towards the left side. Now, using this rule, we can find HA. To draw the shear force diagram, only with the reactions and loads, we can draw free body diagram and find the shear force values. These are the shear force values for the column AB. These are the shear force values for the beam BC. And these are the shear force values for the column CD. Here you can see the shear force diagram. In the beam BC, in this point the shear force becomes 0. In this point there will be maximum positive bending moment for BC. We can make a section in this point and find the distance. Here I have drawn the free body diagram with the movements. We know that in this section the shear force becomes 0. We can find the shear force in that section. In this way we will get x, which is 1.3 meter. To find the moments at A and B, we can use the right hand side rule. It is the hinged end, so the moment will be 0. Let us find the bending moment at B. HA is acting in the clockwise direction, so that it will be positive, and the distance is 4. For bending moment at B, we will get a positive value. That means the moment at B is a sagging moment. Now let us find the maximum positive moment in BC. We know that it occurs in this section. MB is acting in the clockwise direction, so that it will be positive. The vertical reaction at B is acting in the clockwise direction, so it is also positive, and the distance is 1.3. The UDL is acting in the anticlockwise direction, so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. Finally, we will get 85.11. To find the moment at C, we can use the left-hand side rule. HD is acting in the clockwise direction, so that it will be negative and the distance is 4. For the moment at C, we will get a negative value. That means the moment is a hogging moment. We know that in the hinged end, the moment will be 0. Here you can see the bending moment diagram. If we make the diagram upside down, that means in the opposite directions, that is called the bending moment diagram on the tension side. Alternatively, easily, we can draw the bending moment diagram by superposition method. For that, first we need to draw the free movement diagram. In the beam BC, we have uniformly distributed load 30 kN per meter. Using this formula, we can find the moment and we can draw this diagram which is in the shape of parabola. We should not consider the nodal point load 45 kN. We know that the moment at B is a sagging moment and the moment at C is a hogging moment. Using the direction of arrows, we can draw the end moment diagram. The sagging moment will be positive and the hogging moment will be negative. Then we can combine both of the diagrams so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.